So this is part one of our acid, base, and salts section. Okay. So what we're going to do today is we're just going to go over the properties of acids and bases. So there are a couple of definitions, the Arrhenius definition and our alternative definition, which is our Brownstead and Lowry. You just have to know that there are two types of definitions. The first one is usually what you'll see on a Regents. The second one you may not see as often. So let's go over what this means. Acids by definition are compounds, usually ionic because they have to split apart, compounds that produce hydrogen. Okay. So this might be considered like this, or you might see it written as H3O, which is a hydronium ion. You might see them in little brackets like this, which indicate that they have concentrations. Okay. And in the case of when they dissolve, these are the only positive ions in solution. So we see this when we talk about hydrogen chloride. Okay. When we put an acid into water, we are actually creating this hydronium ion and a chlorine ion. Okay. And we indicate that they're ions by looking at the positive and the negative. Okay. So we know that in the case of hydrogen chloride, H is being given off, therefore HCl is an acid. Now the alternative definition is a proton donor, meaning that there is some species or some molecule that's giving off the hydrogen. Okay, so we'll call it a proton, which is another word for the H plus ion donor. So we can see this when we're, say, looking at ammonia. Okay, ammonia plus water. I'm going to write it like this just because I want you to see where the H goes. Will actually create an ammonium ion, which you've seen before. Let me fix that. It's going to be an H4, which gives it a positive charge. Okay, and an OH negative ion. Okay. So in this case, the one that is going to be donating, this one is going here, water is considered the acid. Okay. So the key is to just pay attention to the H's. All right. General formula for this, if there's an H in it, it's probably some kind of acid. So look for the H, or you can go to table K. So some examples, go to table K and take a look at it. Now, like we said in the earlier part, these do dissociate, meaning that they are going to conduct electricity. So yes, because they're ions. Now the range is usually from 0 to 7, which we consider neutral. This is going to be a strong acid, and this is going to be a weak side of the acid. So 0, 1, 2, 3, 4, 5, 6. As we are going this way, it is becoming weaker and weaker. Now on the flip side, we have bases. Bases are now looking at this thing called the hydroxide ion. So these are compounds, again, they're ionic, that produce OH negative ions. Okay, so that concentration will change. So, and again, this is called hydroxide. You can see that in your reference table. So some examples of this would be, say, NaOH. Now we're not looking at the H anymore. If we see an OH, we know that this is a base because this is going to dissociate into, again, ions. And those ions are going to be changing the electrical conductivity of that. So in the case of this example, NaOH is a base. The alternative definition, the Bronsted-Lowry, is that this is a proton acceptor. Okay, and when we're talking about proton, it's also talking about just the H, because in a lot of cases there are bases that don't always have an oxygen. So we call this a proton acceptor. Okay. And again, we can also see this in the example that I have for you here. Okay, so who accepted that hydrogen? This guy, right? Okay. So, because this one accepted it, we call this one, ammonia, the base. So in this reaction, we have an acid plus a base making two different types of ions. Okay. General formulas is that you're really looking for the OH negative, and you can also see the good examples in Table L. This 2 will conduct electricity because of the ions. Anything positive or negatively charged will create electrical conductivity. So on the flip side, 7 is considered neutral. So this goes all the way up to 14. Oops, a little bit too close on this side, so let me just get rid of that. Move it in a little bit. So this is considered a strong base. This would be considered a weak base. So as we are counting up from 7, 8, 9, 10, 11, 12, 13, we are now increasing, and the word is kind of tricky. It's called basicity. Okay. This is actually called, on the other side, acidity. And those are the properties of acids and bases. So the general rule, and again, there's acids, there's bases, and there's salts. So when we look at acids and bases, some good examples would be, let's see, acetic acid. That H is going to be given off. HCl, like we said. And then again, looking at table K, you can come up with a whole bunch of them. In this case, this one's highly acidic because it's probably going to give off a lot more hydrogen. So the formula contains an H with a nonmetal. That's the general formula. For bases, we have anything that has an OH, so NaOH. Okay. Calcium hydroxide, which is how you would write it, balanced. And that alternative, which we talked about, that NH3, because this one is going to be the acceptor. More likely than not, it's going to be a metal, as you can see with the calcium, as you can see with the sodium, with an OH. And again, our exception, ammonia, which is a product that we use for cleaning. Okay. Now salts. Salts are everything else. So we're going to give that the orange designation. So we would say sodium fluoride or potassium chloride. Anything that doesn't have a K, doesn't have an OH. So in one of the examples from your last part where we were going over ammonium, ammonium is not a base. Okay? Ammonium nitrate would be another example of that. Now, like we know, it's a metal with a non-metal. Okay, so lots of salts. We could also have the example here, which are polyatomic ions. Anything that is polyatomic, more likely than not, would be considered a salt. Now there are exceptions, and there's always the trigger when we're talking about Regents questions. There are these things called alcohols. So anything that ends in OH but is a hydrocarbon is going to be considered an alcohol. So alcohols can be found on your organics table, which I believe is table R, but don't quote me. Anything that has those amounts. So these are considered non-electrolytes. Anything that has CH and an OH are considered at the end. Okay, so what do they all have in common? Electrolytes. And those that are not are considered non-electrolytes. Hope this helps.